Hi, Bio11A. Let's move on here to the world of water. We've been looking at all sorts of molecules and let's look at some properties. There's a lot of properties of water that make it such a fantastic universal solvent. So the first thing we want to look at is cohesion. What's that mean? It's the tendency of those water molecules to stick to one another. And we talked about that, right? It's because they have hydrogen bonds. They're going to stick to each other. They're going to make they bead up. You drop water on a table, it beads up. So that's cohesion, right? Water molecules stick to one another, not to something else, but to one another. They have cohesion. And then I give you the example of the insects that can actually walk on water. Very cool. Okay, cohesion. Why do we care? I mean, not so much about an insect walking on the water, but it also is going to allow water molecules to be able to climb from the root of a tree to its highest leaves. You ever wonder about that? You water the tree on the bottom, and then the leaf at the very tippy tip, which is really far away, has to obtain that water. How does it climb against gravity and make it all the way up to that leaf on the very tip of a tree or a redwood tree? So this is described here in steps, saying the first thing that happens is there's a lot of evaporation that's going on here in these leaves. So they're losing water, and it's going to create kind of a negative pull here, and it's in all these sort of little waterways that exist within the tree, xylem and phloem. We don't have to talk specifically about what those are. Think of those little canals. And by evaporating, it's going to sort of create a negative pressure in there, and the water molecules that are pulled into the roots are going to want to just climb up, and if they were isolated and didn't stick to each other, they would drop all the way down to the bottom of the tree again. So the reason, cohesion is going to make those molecules stick and allow it as a unit to carry up through the trunk and up to the stems and up to the leaves. Okay, so cohesion is very important in that respect. I'm going to skip this. The other thing we want to say about water is it's a very good solvent, right? We talked about it being polar. So if it's polar, it's going to have a charge. And if it has a charge, it's going to love anything else with a charge, because the negative side of water is going to be attracted to anything positive. The positive side of water is going to be attracted to anything that's negative. So it's going to be a very good solvent, something that can dissolve anything else. In other words, surround it. In chemistry, to dissolve really is to surround that molecule with the water molecules. So solutes that are hydrophilic or water-loving. Philic is to love, water-loving. Water is going to be able to attract to anything that's water-loving, and water-loving has to be polar, has to be something that's polar. If you have a charge, you're good. You're going to be able to get along with water. If you don't have a charge, you will never get along with water. Okay? So this is a really good example. Take a minute to look at this. I won't say a word. What's happening here? We have a chlorine atom. It's negative. It's separated from the sodium, so it's got an extra electron here, this lost one, so it's positive. So it has a charge. Charge. What happens? Well, if I have a negative charge, these water molecules are going to flip around, and the positive end of the molecule, the one with the hydrogen, is going to be very attracted to negative. So hydrogen, very attracted to negative. Hydrogen attracted to negative, and they're going to surround this. Water loving, right? It's going to be able to be surrounded by water. What if that other atom is positive? Well, then look what this molecule does. It flips. And the oxygen end that's more negative is going to be attracted to the positive. So oxygen end attracted, oxygen end more attracted, and it surrounds this molecule. So we say these two get along with water. Yeah, they get along because they are polar, they have a charge, and so does water, and they will be able to be surrounded by that water. They are water soluble. You know this from when you do things like dishes. You try and wash that butter dish with cold water and no soap, nothing is going to happen. Why? Because all those fats are not soluble, they're not polar, they're not soluble in water, and water cannot wash them off, and it's just repelled. However, if something was soluble and it had a charge, you'd be able to wash it off easily because water will surround it. Okay, so water solubility is something that even though you don't talk about, you're seeing that every day in your life. Okay, another phenomenon of water is that it regulates temperature. How so? Well, hydrogen bonds that are sticking one molecule to another make water resist changes in temperature, so it doesn't heat up or cool down as easily when you have these hydrogen bonds. And so we know that as the ocean temperature doesn't fluctuate with the air temperature, you know, if it's 70 degrees out, the ocean isn't 70 degrees. Wouldn't that be nice? So these bonds are going to be able to resist that temperature, and they're going to be able to keep that cool temperature of water, which is probably like, what, 52, 54 around here? That's what it is. Very important. Water also does not dissolve hydrophobic water-fearing solids. You know that. You put oil in water, they're not going to mix. And why is that? Because the water continues having charge, but the oil does not have a charge, and there is no way water can surround it because it can't be attracted to anything that does not have a charge. Now, this one's very cool. We know water freezes. That's correct. Water freezes, and what happens is that the distance between the molecules changes. I'm going to say it again. The distance between the water molecules changes. So look at what these molecules look like in a circle here of liquid water. There's how many? I don't know, 2, 4, 6, 8, 10. Look how many of these molecules are in here when it's liquid. And then if it gets too cold, they separate out. They move away from each other. They move away from each other and form these hexagonal patterns. And then all of a sudden, they become much more spaced away from each other. And by spacing away from each other, then we have fewer in the circle, right? Here I can count them. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And there's many more here. So this frozen water, which is ice, is less dense. It's got fewer molecules in it. So it's going to float. It's got lower density than water. Very weird to think of that, because usually you think of something solid as being heavier and it goes to the bottom. You put a coin in water, it's going to go down to the bottom. But frozen water, which is ice, is also solid and it does not go to the bottom, it goes to the top. And that's because the distance between the molecules has increased, making that area then have fewer molecules and be lighter than that one with more molecules. So ice is less dense than liquid water, and it's a good thing too, because that way aquatic life can survive winter under the ice cap. So we have things freezing at the top, and we can still continue having a whole ecosystem under the ice. If it was backwards, this poor turtle down here and all these fish would be frozen, and then there'd be some things floating on the top, but we would freeze from the bottom to the top. And that's not good. This way, we form this layer of ice, but still you have all this other region of water that's not frozen. Less dense, more dense. Ice floats. Very weird. Let's do this. A substance that's not soluble in water is said to be hydrophobic. Hydrophobic. Which property contributes to the high surface tension of water? Surface tension meaning that insect can walk on the top. Is it hydrogen bonding? Is it polar covalent bonds? Is it cohesion? Is it polar covalent bonds and cohesion? I'm not going to tell you. You're going to have to figure that out. And that's where we're going to stop. Next come the organic molecules, and we'll start out with the carbohydrates. Thanks for listening.